In this lecture, we'll look at JS prototypes, which hold properties that are common to all objects of a JS class like string or number. In the example code in the diagram here, we'll start by modifying functions in a library object the way we did in the last lecture of the objects topic. Now, on line 4, as you can see here, we replace string x's uppercase or two uppercase function with a function that just prints x is uppercase. And then we use it on line 6 as the output down here shows. And on line 5, we confirm the existence of the two uppercase property in x via a standard function of all objects, hasOwnProperty, which is passed a property name and returns true if that property is present in the object. And the output from it confirms that indeed x has a two uppercase property. Okay, now on line 8, we're going to delete this two uppercase function. Now at this point, having displaced the original two uppercase and then deleted its replacement, we might expect that x's two uppercase property would be undefined. But the call on line 9 instead shows that the original two uppercase is back. With a capital alpha being printed out there. And yet the hasOwnProperty call on line 10 in fact shows that x does not have a two uppercase property anymore. It's not present there. So what is going on? Well, down at the bottom of the slide here is a diagram that shows what has happened. Now don't try to understand the whole thing just yet. We'll explain it step by step during the lecture, and I'll black out the top part to keep it from being too distracting for the moment. The missing fact we need to know is that every object has a property typically called I'll just call it proto from now on, which points to another object that is the first object's prototype. The x object here, the string object, points to a prototype here, which has constructor and two uppercase properties. The prototype acts as a backup object or a default object. If we attempt to access a property, either function or data, that is not present, say here in x, then the object defers our request to its prototype. And if the prototype has the property, then the prototype's property is used as a backup. And all objects created by a given constructor, for instance all string objects, share a common prototype object unless you take special action to change that. So in the diagram we show string targets of x and of y pointing to the same prototype, which we label the string prototype. In fact, none of our string objects has ever had a two uppercase method unless we hand added it as on line 4. It is the shared string prototype that has this method, and all our uses of the method thus far have been deferred to the prototype, except for the one case where we overrode it for x. If we give an object its own version of a property, like we did for x.toUppercase, then that version takes precedence over the prototype's version. So if we have a property there, then that takes precedence, as it did when we called x.toUppercase on line 6. And as shown by the dashed arrow, from x's target to the two uppercase alternate 1 function, which shows the situation that was in effect from lines 4 to 8 of the code, when we temporarily replaced x's two uppercase function. But the prototype is still waiting there in the background, waiting to take over again if the object's property is deleted, as we saw on line 9. So if this goes away, then that one is there again. Now, based on what we've seen so far, here's lecture question 1. What statement would you need to make in order for x.toUppercase to actually be totally undefined and to result then in a runtime error without changing x itself? The answer is, what you'd have to do is delete x.proto.toUppercase, and that would wipe it out of the string prototype. Now you've killed the main instance of toUppercase, and there'll be nothing to fall back on. So here's question 2. If you did that, would quote hello quote dot to uppercase still work? Back from a pause. No, it wouldn't work. You'd be calling the to uppercase method on a temporary string wrapper object. And that string wrapper object would share the same to uppercase impaired prototype as all the other string objects. Once you've modified the prototype for one string, you've modified it for all of them. Now, these last two questions are not just academic. They show that it is possible to dynamically modify the prototypes themselves and thus affect all objects sharing that prototype. Let's look more closely at that. On line 12, we replace the string prototypes to uppercase property. Now, the diagram shows the original to uppercase function down here, pointed to by a dashed line arrow, and that's the way it was. And now there's a solid arrow from to uppercase to the alternate version of our to uppercase function instead, and that's the way it is now after the assignment. Now, as the output back up in the code on lines 14 and 15 show, both x and y have now been altered. They have altered to uppercase behavior since they both defer to their prototype. And as line 18's output shows, very importantly here, even a new string z, which is declared on line 17, of course, also sees this change. That one also has proto-uppercase, because all objects created by the string constructor share the same prototype. Now, before we go too much further, I need to appease the gods of modern JS by pointing out that while all objects do have a property indicating their prototype, and that property is almost universally called proto, that particular name is an internal implementation detail of each JS interpreter, thus its funny spelling. All major interpreters and browsers agree on that name, but future JS interpreters reserve the right to change this implementation detail, especially because optimizing a JS interpreter can require some cleverness surrounding how prototypes are tracked. So the direct use of the name proto is deprecated, and in some future JS implementations it may no longer work. The reliable alternative is to use the method object.getPrototypeOf, passing it x, as we show on line 13 here, and this does the same thing as x.proto, but is not vulnerable to internal design changes. So line 13 shows such a use, and would have had the same effect as this code here on line 12. It returns the prototype of x. Now, from here on, I'll avoid using proto in the code, and in the lecture I will usually refer to just an object's prototype, meaning the target of its proto property. But the diagrams will still show the proto property because we need some way to label the internal reference each object has to its prototype. In your own JS code, be aware that each object has a proto property or some functional equivalent of it, but always use object.getPrototypeOf and other related functions that we'll introduce to deal with the prototype. Don't refer to proto directly. Prototypes let you standardize all objects created by a constructor, providing one shared copy of all the functions without having to make them properties of every object. All that's necessary is to correctly set the prototype of each constructed object. But how does each new object's prototype get initialized? Now, as the diagram down here shows, the string constructor function includes a property named prototype referring to the shared prototype of all strings. Most constructor functions supply such a property, and if it exists, the new operation automatically copies the constructor's prototype property into the proto property of each new object created by it. The name of this constructor property is a bit confusing. The property is not the prototype of the constructor, but of its created objects. It should have been named model prototype or something like that, but as with other JS oddities, we're stuck with it now. So to summarize, under proto is a reference that every object has pointing to its prototype. prototype is a reference in constructor functions used to set up the prototype of any object they construct. Be sure you understand that both equality checks on lines 20 and 21 are true per the discussion we just had. Object get prototype of z is the same as the prototype of x, and the prototype of x is the same as string.prototype. Now, if you want to change the properties of the prototype shared by all objects created by a constructor, you can use the constructor's prototype property to do so, as on line 23 here, where we add a one more function property to number.prototype. And this function returns its context objects plus 1. Now all numbers have this function via their prototype, and so do elemental numbers by virtue of being wrapped in a number object. So, for instance, on line 25, we call one more on number I and on the constant 42, and we get the expected output of 2 and 43. Now, question 3. Would swapping lines 23 and 24, putting the construction of I first before we change the prototype, would that have changed the output of line 25? And returning from a pause there, well, no. Even existing number objects will see the new one more property since they all share the same prototype. So I would have the one more property in its prototype even if we created it before line 23, once line 23 was executed. You can spontaneously add a function to all existing objects of a class by modifying the prototype, and it's not uncommon for JS code to do so. Now, to complete the circle of references here, each prototype is also given a property called constructor. And this refers back to the corresponding constructor function, as shown in the diagram here. So, both equalities in the constructor check here from lines 27 to 28 are true. Generally, object.constructor.prototype is a synonym for object.getPrototypeOf, assuming you haven't done something ghastly like changing the proto property after construction. And by the way, doing so is a grave sin in JavaScript. We'll have more on that in a later lecture segment. Okay, and then the final major point here. We said earlier that all objects have a has-own property method. But using that very method to check for its own existence as a property of x on line 33 produces false. Okay, well that really shouldn't be a surprise by now. Has-own property is probably in x's prototype, not x itself. But a check of that, we assigned x's prototype into xproto here and use it on line 34, that also produces false. So now what's going on? Well, the further detail is that prototypes also have prototypes of their own. They're objects, after all. And again, all objects have a prototype. So if prototypes lack a property, they in turn defer to their own prototype. So I just removed that blacked out box to show the entire diagram, and we can see that each prototype, like string prototype, has a proto property referencing another prototype, forming a sort of prototype chain. So the check on line 35 down here reaches all the way to x's grand prototype, so to speak, and we find the has-own property function, or has-own property function, is there. Now that grand prototype is the object prototype. This is string prototype's parent prototype because string, like other JS built-in types, is derived from object. We'll look more closely at what derived means in JavaScript in the next lecture, but from the diagram it apparently involves the derived class's prototype pointing to the base class's prototype. So where does this prototype chain stop? Is there a x.underproto.underproto.underproto, or does the recursion end somewhere? It stops with the object prototype, which is sort of the granddaddy prototype object. And this is where has-own-property and various other universally applicable functions are found. And object.prototype's prototype is null, as the diagram shows. So the buck stops there. And question 4, is this the first time in this particular program that chain of references, x.proto.proto, has been followed? And if not, then what other lines of code followed it? Turning from a pause, well, any call of has-own-property must have followed it in order to find the has-own-property function to call it. So lines where we called has-own-property followed that prototype chain.